children, welcome to your chemistry online class. Last class we have discussed about the types of cubic lattices, types of unit cell, etc. And we learned more about the crystal structure and all. We know matter can exist in three forms: gases, liquids and solids. We are learning about solids. How the atoms or ions or molecules are arranged in a solid. We know it is perfectly packed. If you go to fruit shop, you can see the fruits are arranged in a systematic manner in order to avoid vacant spaces. Similar way, for our study, we are considering the atoms, ions or molecules in a solid in the form of solid sphere. So we'll see how the molecules or atoms or ions are arranged in a solid structure. In order to avoid the vacant spaces, the atoms are arranged in a closely packed manner. This arrangement is known as close packing arrangement. Close packing. So in solids, the atoms are arranged in closely packed. So it is packed together. So we can use the available space most economically. So this is known as close packing. And one more thing is there, coordination number. What do you mean by coordination number? While packing the atoms, how many atoms are touching each other, or one atom touching how many atoms? This is known as coordination number. If we take this third atom, it is touching 2 atoms. So, its coordination number is 2. Similar way, we can identify coordination number for different close packing. The close packing can be done by different manner. We'll see how the atoms arranged in solids in 1 dimension, 2 dimension and 3 dimension. First we'll go to 1 dimension. If we take 1 dimensional structure, the only possible way that we can arrange them like 1 dimension only. So either x-axis or y-axis or z-axis. So as a single unit only or as a row only, we can arrange the particles in 1 dimensional. So only one layer will be there, or either we can arrange like this, but only one layer will be there, only a layer. So this is 1 dimensional. So the coordination number will be 2. Atom will be touched by 2 nearby atoms. This is the 1 dimensional arrangement. So what will be 2 dimensional arrangement? We'll see that. How the 2 dimensional arrangement will be. The 2 dimensional arrangement will be is in 2 type. Those are square close packing and hexagonal close packing. Square close packing and hexagonal close packing. We'll see what is the square close packing and hexagonal close packing. So, we have seen the 1 dimensional model. 1 dimensional atoms are arranged in a 1 layer. So, what will be 2 dimensional? In 2 dimensional, we know 2 dimension will be there, x and y or y z, etc. So 2 dimensional, one more axis will be there. So we can arrange it by two way, either by touching each atoms. It's two dimensional. Like this manner we can arrange atoms. This is one type. So if we see here, we can see that one atom touching by four atoms. So it is in the square type. Square. So this is square close packing. Then what will be the hexagonal close packing? We'll see that. Atoms are arranged in one dimensional, then we'll move to the two dimensional. So in the structure, in hexagon square close packing, one atoms directly arranged in the same row. But in the case of hexagonal close packing, we know there will be a gap between two atoms. In the gap, if we can arrange the atoms, if you see here, so this is A type, A layer, and we are adding B layer to this. And if we again adding A layer, here one will become here like this manner. We can arrange the atoms. So in between the gaps, we are arranging the atoms. And if we touch here, if we count the numbers which touching, we'll get 1, 2, 3, 4. It is in the hexagonal structure. You can see a hexagonal structure here. So this is the hexagonal close packing. So if we arrange the atoms in the hexagonal model, we can efficiently pack. We can avoid the vacant spaces. So the hexagonal close packing is more orderly packed. And these depressions, we are packing in the depressions. You can see here some this is the packing in the two dimension, either square or hexagonal. And we'll move to the third type, that is three dimensional close packing. Three-dimensional packed structure is obtained by arranging hexagonal close packed layers one over there. We know hexagonal is more economical, so hexagonal layer is arranged over by the over. So we have seen the two-dimensional packing. Now we'll see the three-dimensional packing. So here we can see already the two-dimensional packing. So we can arrange by arranging layers like this. So we can exactly arrange like this. So only one type of atoms are there or one type of layers are there. So it is known as AAA type. Then we'll see the hexagonal close packing. How will the hexagonal close packing? Here you can see the alignment A, and there are two types of voids. What do you mean by voids? The voids are the gap While arranging the atoms, you can see some gaps. These gaps are known as voids. If the number of voids increases, the packing efficiency decreases. So these are the voids. Here you can see two types of voids. Those are upward triangles and downward triangles. Green color indicating upward, white color downwards. So if we put on the upward voids, we'll get like this. If you are arranging a layer exactly on the upward, we'll get like this. We'll get two types of voids. This octahedral voids, tetrahedral voids and octahedral voids. You get two types of gaps, tetrahedral voids and octahedral voids. You see the arrangement, we'll get an idea. So layer A and layer B are here. And if you are seeing this one, we know 3 atoms of layer A will be there and 1 atom we'll put on the gap. So we'll get a tetrahedral structure. Thus it is known as tetrahedral void. The 4 atoms are touching each other. So the coordination number is 4. This is tetrahedral void. And how the octahedral void forming? So if you are putting the layer above the 3 atoms, we'll get an octahedron. So this structure is octahedron. So that type of voids is known as octahedral voids. So tetrahedral voids also will be there and octahedral voids also will be there. So if you are putting the another third layer, or we'll get another third layer, that is C layer or AB type also will be there. First and third layer have same alignment. And we'll see what type of cubic structure we'll get. So in the hexagonal close packing, we have seen that it is AB type. So start with a layer of identical spheres and the triangles, the voids which are closed by another layer, that's B type, and third layer is in the top of the first layer. So first layer and third layer are similar. It's AB types layers. Then we'll see cubic close packing. It's denoted by CCP, cubic close packing. How this cubic close packing is arranged? In this type of packing, the third layer is placed in such a way that the particle cover the octahedral voids. There we have covered the tetrahedral voids, but here the third layer is covering using octahedral voids. So we are covering the octahedral voids here. So in the hexagonal close packing, that is denoted by the letter HCP, in this type, the third layer placed such a way that the particles cover the tetrahedral voids. Here, tetrahedral voids are covered by the third layer. So it is AB type. Examples: molybdenum, magnesium, beryllium, zinc. And cubic close structure. Here we are covering the octahedral voids. The third layer, that is C layer. Here the third layer is not similar with the first layer. So it is covering the octahedral voids. In this type, the packing of the third layer is placed in such a way that the particles cover the octahedral voids. So it is different from first layer A, second layer B, and it is C layer, third layer. If further layers added, it will be in the form ABC, ABC, whereas HCP will be AB, AB. Examples are iron, nickel, copper, etc. And the gaps between these layers are the interstitial sides are known as voids. We'll see the packing efficiency in the next class. Thank you.